This is the first session of the visual neuroscience course. Thanks for your interest. I am very glad to see so many people showing interest in the vision course. The idea primarily was for our postbacks, Karen and Tim and Emily, who are here. But look what we have. Everybody is here, and I hope this will be a productive period for us all. This is not a classical course by any definition. We are at NIH, so there is no mandatory course for you guys, or there's no credits. So we are just doing this for fun, basically. During the sessions, I like to keep it informal and unorganized, as unorganized as possible, in the sense that I don't want to police the sessions. So feel free to jump in and ask your questions during the back and forth. If we happen to sort of get complications with sort of speed and we are stopped too many times, then we think of a method to organize questions. But for the moment, let's just be wild. And whenever you have a burning question, speak up. One thing that I want to communicate up front is that, especially for the postbacks, I want you guys to talk. So this is not a radio show. This is not a podcast. This is an interactive course. So I would love to hear your feedback and your questions. And don't feel no question is a stupid question. But every question is valid, and just feel confident about your questions. Jump in and ask. So with that introduction, let's go ahead and start. Do you see my screen? Yep.
Yeah.
Excellent. Excellent. So I want to start this course with, oh, wait a minute. I need to find my cursor. I don't see my cursor. Wait a minute. How do I make my cursor active when my slides are up?
If you go to your view options,
My view.
I think you should be able to turn on a laser pointer.
Laser pointer. Is it called laser pointer?
I don't know.
Pointer. Okay, it's let's see.
I see your mouse. I see your mouse.
Yeah, but once I go into the presentation mode, I don't think you can see it anymore. Now you don't see it. And that's weird. Okay, let's well, we'll do it Greek way, words. Let's see if I can point to spots on the screen with words. All right. So this session is about the computational problem of vision, and I want to. This is not mainstream by any means. This is basically, I want to find a way in this session to communicate the core computational problem of vision in a language which is not intimidating, or it's not overtly mathematical, and it's mostly conceptual. And at the same time, I don't want to fall into the trap of conventional definitions of computational problem of vision, because there are some approaches, mainstream approaches in our time, that are super important, and we will talk about them. But I want the scope to be bigger than that, the horizon to be bigger than what we are taking as computational vision right now at this moment in history. So I start the course with this letter. This is from MIT archives, July 7, 1966. I was -8 years old at that time. And so this is, let's read through it. Rosa, can you read through this for us?
Sure. Can you hear me?
Yes.
Okay. The Summer Vision Project. The Summer Vision Project is an attempt to use our summer workers effectively in the construction of a significant part of a visual system. The particular task was chosen partly because it can be segmented into sub-problems, which will allow individuals to work independently and yet participate in the construction of a system complex enough to be a real landmark in the development of pattern recognition.
Excellent. So they thought it's a summer project. The idea, this is 1966, and people are getting interested. The ideas of computational approach to vision is rising, and at MIT they are like, okay, we are MIT, let's do it, let's solve it in a summer. And this is how many years passed, many decades passed, and yet here we are. The problem is not solved yet. But what made them think that it could be that easy, and what happened since then? Like, how did we realize what were the problems, and what we've been doing since then is basically part of the message that I want to communicate in this course. So let's go back in time, a little further back than 1966. Let's go to like minus 500 BC, ancient Greece, Plato's time. The notion of Platonic cave, if you're familiar with it, it's the idea of a cave. This is a cross section of a cave. Then somebody is sitting at the back of the cave with his back to the entry of the cave. According to the actual allegory, he's chained there, so he cannot really turn around and see the actual images back there. There is a source of light, and somebody is holding an object, and he sees the shadow of that object on the back of the cave. And the idea of Platonic cave or cave allegory is that how would you know what is really out there by looking only at the shadows? And you basically, the idea of Plato is that you will miss the actual things that are happening in the world. And in our world, we are in a cave, so we are looking at the shadows of the real things, and how is it that we can find what those real things are. So so this notion has a similarity to the situation, to the problem of vision, to the computational problem of vision. Imagine your skull is the Platonic cave. There is a closed box, no light goes in there, and your brain is sitting there right there in the dark at the moment as you talk to me, as you see me. And let's turn off the lights just to gain more space. And so what does go in there? What does go into the dark cave of your brain? Definitely no light, but there are two optic nerves. But what does I mean? What visually goes in there? There are two cables, the optic nerves. Those are the things that go in. Do they carry light? No, they don't carry light. They carry signals. And in what form? Each one of them is a cable, contains about 1 million wires in it, 1 million axons in it. And that's basically getting refreshed constantly and sending numbers up there. So every second you move your eyes 3 times, so those numbers change. And the world in front of you changes constantly, those numbers change. And the light, the lightness, the light power around you gets more or less, it gets lighter or darker, those numbers change. People move in front of you, those numbers change. Those numbers are all what you have. That's your visual world. So now the question is, imagine you've got that. Imagine you've got a snapshot of the numbers that are being sent to your brain. What does your brain do to that? Like, how would you extract any information from that? That is the computational problem of vision. This is a matrix which is highly unstable. It's a matrix that as you move your eyes, the matrix changes. The numbers on the matrix change. As you turn your head, the matrix changes. As things in the world move, the matrix changes. Even if nothing moves, only the light, like the sun goes up or down, the matrix changes. So how do you recognize familiar, let's say, people or objects or food, or how do you navigate? These are all like basically boiled down to the question of how do you deal with those numbers? What do you do with them? So David Marr, around that same time of like I would say, I don't know, I don't like to call it golden age of vision. That's the birth time of vision as a science, but quite immature, still immature. But very exciting time in vision science, definitely. This is the idea of computation, processing, or getting into the vision science. So he coined this term cold reality. And we are going to refer to it as maybe slightly different definition than what Dave Marr said, but more or less the same concept. The idea is that cold reality is what those numbers are read from. Cold reality is out there. It doesn't have any meaning. It doesn't have light. It doesn't have color. It doesn't have shape. It doesn't have any of those things. That's the physical reality. And your eyes, your brain is making contact with that cold reality through this matrix, through these numbers. So this matrix of numbers. So these numbers are what you get from that, your interaction with cold reality, right? Light touches the cold reality, reflects back to your eyes, activates these sensors back of your eyes, and they send these numbers to your brain. Now you have to give life to this cold reality. You have to warm it up, in Dave Marr's terminology. What does it mean to warm it up? It means to give meaning to it. You've heard this, perhaps you've heard this almost, I mean, not almost, purely philosophical notion that if a tree falls in the forest and no one is there to hear, does it make a sound? So the idea is that maybe if there is no one to hear it, what is sound? Sound is something which is defined by the observer interacting with the stimulus, so there is no sound. So that philosophical version sounds too abstract. What do you mean? The tree falls and it creates vibrations. The physical laws work, and the waves of vibration pass through the air, right? Okay, don't call it sound. But there is another thing. The other thing is that, yeah, the wave happens, the vibrations happen, but sound, the sense of sound, hearing the sound, is different from physical vibrations. The sense of lightness, the sense of seeing light and how bright that light is a subjective feeling that you attach to those numbers. It is not exactly those. We will talk a lot about that, but to just give you a sense, so let's say that's the matrix you want to work with, right? You're like, okay, let's see. The first thing I realize here, perhaps the first principal component in a sense, is that these numbers vary. They go up, they go down. They have a range, and they can be small numbers and large numbers. And the small numbers tend to move around as I move around my eyes, even in the same patch of this matrix, and the high numbers also. So what do? I make up this concept of brightness and basically read those numbers and convert them to the idea of brightness. Do I do it mindlessly, in a sense that let's say the number is whatever, at that point in that the top square, the number is 8. Let's say whatever unit, it should be a unit of light energy, right? 8 candela per square meters. How bright is that? Do I perceive things that are having higher numbers, higher energy, as brighter linearly? Well, we know that's not the case. we know from long time ago, in fact, from the sort of late 19th century, that the amount of luminance, the amount of energy that you push into the eyes is not linearly predicting the brightness. Or brightness is one of those words, right? These words are, in common English, these words are synonym, basically. So we define them. Luminance is the amount of energy which is hitting your eyes from the object. Brightness is perceived luminance, is like, how do you perceive that luminance? And what you realize is that as you increase the luminance, the brightness starts to saturate. It follows a logarithmic curve, and it's not a line. This is perhaps one of the most fundamental laws of vision, that luminance is not brightness. Luminance is converted to brightness somehow. This handsome dude is the one who discovered this. And after him, we named this the Fechner law, although this other handsome gentleman should not be ignored, Ernst Weber, and I recommend looking him up. They have Wikipedia pages. It's quite easy to look them up. They are mainstream, and they made serious contributions, in a sense, in understanding that perception of light is not reflection of light energy directly. We are basically passing it through a function through our brains. And why do we do that? Why don't I systematically perceive something that gives me a bigger number in the eye as brighter? Why don't I do that? Because it has a function, and we will talk about that function in the later on. But the point that I want to communicate at this stage is that everything done in vision is for its function. We are extracting information, useful information to act upon from that matrix from very, very early on, the first stages of processing that information. As a matter of fact, if I have somewhere in my brain that I have that matrix represented exactly as it entered my eyes, it means that up to that point in my brain, I have done nothing on that signal, right? Nothing is extracted from that. It's a useless signal, basically. All right. So let's say we extracted luminance from that. Then what? We are more in vision is a geometric sense, unlike audition, which is basically not as geometric as vision, because the sounds refraction doesn't give you that accuracy. But vision is a very geometrical sense. There's a lot of geometric information protected in that matrix that we are looking at. So you start looking at this. Okay, what can I do with that? Look at that. It appears that there are some boundaries in there. Look at the numbers. Check the numbers. There are some boundaries of high numbers and low numbers. These numbers are not a random mix of numbers, right? It's not that you have put high numbers and low numbers in a bag, shaked it, and then reorganize them on the screen. They are clustered. That's a property of the matrices that come into your eyes, reflecting the property of natural image. So, of course, the first thing to start to do with that is that, okay, let's extract those places. Let's make an operator. Let's make an operator, and we will talk about this operator later in the course. These are called Gabor filters, and we will talk in details about them. But the idea is that these are stuff that pull out the orientation and spatial frequency, but just for the simplicity, they pull out the orientation signals from that matrix of numbers. So do we understand what's going on there? What does it look like, this number? Does anybody know what is that? Can you tell? A bunch of numbers. Okay, so we can go even crazier. We can say, I mean, we are still in our we are still in our 66 summer project at MIT, right? It's like these are the things that you could do back then. And you're like, okay, let's say this is not 66, this is 2000s, so I have more computational power, maybe I can do something else with this, maybe more than pulling out the actual edges, I can start digging more information out. Like there are these islands of numbers like that are basically more or less similar numbers, darker shades in the background of lighter stuff. So let's detect those. They seem to be a structure, and I am looking at a structure. I want to detect the structures in this system in my Platonic cave to understand what was out there, right? I can go even wilder and say, let's go even like one step higher. I detect the, let's say, islands in there, and then I make structures that look at the relationship between those islands. Like how do those islands relate to each other? And now I make up a detector which is now beeping whenever a given particular combination or arrangement of lines and circles are in the signal, right? Okay, so basically what my visual system does from the earliest stage of visual processing is to operate these functions on the signal to pull out information from it, to pull out descriptors that can guide behavior, that can guide perception. And by perception, I mean behavior. So hopefully, we are not there yet, but hopefully at some point, we will get to a point to actually be able to describe that matrix of number the way they really are, right? So the way the brain does it is that not only it starts from extracting the edges, it starts from making up descriptors that describe the image, let's say in this case in the form of a face, and then there is more. There is like, oh, look at those cracks. This painting has lots of darn cracks on it. What is a crack? It's a high-level descriptor, right? I just used it to describe something that we both know what that thing is, right? If you go back to the original matrix, a crack is a mathematical function, right? It's a way that those numbers behave, and then you kind of name it a crack. So you have to detect the cracks, basically, or you have to detect a smile, you have to categorize a smile, and all that, And uh, and one thing that we should remember is that this is very dependent on the way your brain does it, right? So the cold reality of Mona Lisa is out there, is sitting in Louvre. So if I look at that, I see something. If a crow sitting on my shoulder look at Mona Lisa, it's same signal, it's same physics, same optics. The crow would see something totally different, right? The crow would probably think, okay, where I can sit on it, okay, the top of it is probably more prominent, that kind of thing. The stuff that matter for the crow are pulled out of the matrix of numbers for the crow. So in a sense, perception is an interaction between the physical reality and the brain that is analyzing it. So this problem has been formulated in many different ways. One of them which is worthy of mentioning is by Gibson. We are even further back in time. I mean, not as much as the ancient Greece, but 1950. Gibson coined this term inverse problem. So the inverse problem is as follows. A retina is a two-dimensional surface, and world is a three-dimensional entity. So, and you have the optics working on to sort of create a picture, a projection of the three-dimensional world on a 2D plane. information is lost. Now what you want to do is that you take this 2D image and go back and reconstruct the 3D stimulus out there, right? How can you do that? In the Mona Lisa case, well, honestly, we didn't go that far, right? We talked just about segmenting the image into the its features and stuff like that. But the problem is actually bigger. The problem is that that matrix of numbers could be coming from multiple different things. Which one of them is that I am perceiving? For example, if you have a retinal projection that shows that whatever, like vertical red line on the retina, what does it correspond out there in the real world? It could be a pencil. It could be a massive electric post far, far away from you. It's just farther away, so its angular size is the same. It could be a tilted line. It could be many things that all of them have that solution. All of them, once they go through this projection, they give you the same projection. How do you undo that loss of information? This is the inverse problem. This is another formulation of what we talked about earlier. And inverse problem is important in a sense that the way I formulated the Mona Lisa problem for you guys is as if you have those numbers and you do your job really well, put 5 summers on it, you'll solve it. The problem is there. The solution is there in the numbers. You find a way to define faces, you find a way to define people, mountains, and things like that. But that is a little simplified compared to the real problem that we are dealing with. Information that is in the signal is not enough to make sense of it. The information that is in the signal is impoverished. It's gone. It's like part of it is lost, and to recover that, to recover the actual basically physical cold reality, or to estimate the cold reality, now I need to use lots of assumptions about the world. Without those assumptions, vision won't work. So this is the other thing that I want to communicate with you guys, that vision is not possible if you don't have prejudgments about the world. If you don't have assumptions about how the world works, you can't see. As simple as that. So let's do a game with each other. Let's play a game. This is a weird shape, like resembles an eye, a big eye. So I want you to fixate at the red dot at the center and keep your eye there. I'll count 1 minute as we all fixate there. Don't move your eyes. And don't move your distance from the monitor. Try to keep it at one position on your retina and keep looking. So as you look, I explain what will happen, but don't look anywhere else. So what is happening right now is that an image is cast on your retina, and this image has dark and white, right? The white parts are making your retinal cells active, your retinal rods and cones, rods mostly active. And so they are firing. Those neurons are sending this matrix of high numbers to your brain. The dark parts, the black parts, are getting much less light. So they get the low numbers. They don't get activated as much. So as you keep looking, please keep looking, and it might look a little weird after looking at it. You might see edges around it. So what is happening now is that your retina is getting tired. The neurons that have been firing, the neurons that have been in the light area, are getting tired. They're running out of chemicals. But the neurons that are in the black area are fresh. They have not been used that much. So if I do in a few seconds, and just keep your eyes more on that for the last few seconds, so now basically that image is burned on your retina. If I switch to a flat white scene, this is what will happen. Keep an eye on that, and now we go. So blink, 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 blink. Do you see the eye bright and shiny around the red dot? You see it. Everybody sees that, right? So keep blinking. You still have it. You still have it. Go very close to the monitor and find it again. Very close. It gets small. It gets teeny tiny. Everybody sees that? Okay, let's reinforce now. Reinforce. Just look at it for 10 more seconds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, find it. Blink, blink, blink. Now look at the wall. Look at the wall or ceiling, far, far from you. Is it big? Does everybody see it? Blink. If you blink fast, you find it. Yeah?
Yeah.
So go ahead. Yeah.
I was going to ask, does anyone else have a surface that's curved or like a corner? Because mine is projected around a corner.
That's actually fun to project it around the corner.
Yeah, it actually takes the shape. Yeah.
It takes the shape, right? Yeah. Okay. Wait a minute. What's going on? I thought vision is about what's on my eyes. This is burnt on my eyes. This is actually, we burnt it on the retina. The size of it does not change at all, right? But the context matters. If you're looking at something very close and something is, let's say 5 millimeters on your retina, that's going to be a teeny tiny thing. If you're looking at a far, far, far scene and something is 5 millimeters on your retina, that is gigantic. That's a huge, huge object that still have occupies 5 millimeters on your retina. So you have to make sense of the retinal activation based on your other assumptions about the world, like how far is the thing that you're looking at, right? I was actually making these slides last night and I tried it in the dark, and that's also another interesting experience because this gives you a notion of what is your default assumption of distance. Like the size that you perceive is basically telling you what is the default of your eyes, like how far things are from you. But I'm bringing this up to mention, this is called Emert's law, that the size of an retinal after image is scaled with the distance of the surface on which it is perceived on. So we see here that something as simple as size is not retinally bound. It is active, and it is the brain should actively make sense of that.
Can I ask a quick? Oh, I just wanted to say that it was weird because my after image is like slanted.
Aha!
So that's
because your head probably was slanted when you burned it.
Oh, now I don't remember, but
yeah.
Slanted, but maybe.
Yeah. Actually, let's set up another rule. Everybody who speaks up, can you please say your name? So little by little, initially I thought that everybody go around the room and introduce themselves, but then I thought that's lame because it burns a lot of time and we will forget. But in the context of conversations, we will learn. So from now on, everybody who speaks up, just mention your name so that we get friends, make friends with each other. And can I ask your name?
Oh, my name is Malcolm.
Malcolm. Okay, yeah, that was a good observation.
Right, thank you.
Arash, could I since we're stopped for a question, could I just throw in one question, please? This is Shruti Jappi.
Please.
So presumably this happens through learning, right? This context, imposing a context. This would not happen in a brand new retina / brain, right? A newborn, for example, would not, if you had a newborn staring at this picture that you did and then have them look away and you had some way of figuring out what they are seeing, it would not be how we perceive it, correct?
Probably. There still remains a question. This is, you're poking at the old nature-nurture debate at the end of the day, right?
Yes.
And we don't really have the answer to that question for some reasons. But what we can tell for sure is that a big part of it is learning. at least. A big part of it is learning. The parts of it could still be in your evolutionary learning, in a sense. This could be something that we have learned in the evolution and is hardwired in our brains, could be. There is this beautiful project that Pawan Sinha is doing at MIT. They go and find people who have been blind and treat them. I mean, some of them you can, like, for example, the cases of if some corneal problem or lens problem has caused the blindness, then you can actually go and fix it with a simple surgery. Unfortunately, in this case, he says some of these are really poor people who just need a pair of glasses, and they're like legally blind from birth and never had the money to buy a pair of glasses. So he's doing these experiments on like the first times that they see things. What do they see? And look up those videos. They are interesting. Okay. Like one of them was they showed them I don't remember on top of my head, but I guess it was a square. And they told him, what is that? He had the notion of light. He could discriminate between light and dark, which is understandable because the eye was not totally darkened, so light would go in. But then in terms of shapes, he had the notion of a corner. He said, I see corners, 1, 2, 3, 4, it's a square. So square was, he did not have the operators that actually pull out the square for him, right? That requires, but maybe edges, maybe corners are more fundamental, more basic, and but that's a great question. We don't really have the answer to it yet.
Thanks, Arash.
Hey, Arash, can I ask a quick question?
Yes,
just to follow
please.
up on that. So
Yes,
as you're
David.
talking about, this is David. So as you're talking about innate processing, because not everything is learned, wasn't it Gibson that had hypothesized that there was something in terms of related to kind of survival in how they process the visual input?
Oh, definitely. The actually, this is. I use this opportunity that you asked this question to say something, which is Mehrdad Jazieri and I. We have this thing, we call it the MIT curse, and it's of course a joke, but we say this is the curse that MIT has put on vision and on vision science. And I should say this again in the context of you know, I think great scientists have this funny effect on history. The greater the scientist, the longer he or she will stop history. Usually it's the case. Like you look at the history of science, good science, amazing scientists are the ones who stop science for centuries. Like Newton, come up with a framework that no one can think out of that box for centuries, right? And stop science. So it's in a good way. I mean, it's an interesting way of thinking about it, right? It's counterintuitive way of thinking about it. By that sense, MIT might have stopped us a little bit, because maybe the solutions that came out of MIT started with David Marr and some other people. The idea, the philosophy is that vision is a universal problem. Vision is it's kind of like machine vision. Machine vision is machine vision. You don't care. The machine should see things. There are invariants in this scene that I have to extract, right? And in that sense, and we made a lot of progress with that formulation of vision, and it is precious. It's really valuable, and we should be able to put it into context, into historical context. It's not that we are against it or for it. That's that's stupid. But one thing that will be missed in that definition of vision as a universal problem is that it is not a universal problem. It's an evolutionary thing. It's a dirty evolutionary trick. at the end of the day. At the end of the day, what is vision good for? We want to move around. We want to eat. We want to escape from predators. We want to, those kind of things that are related to survival are the main drivers of vision. Like if you are a frog, you have bug detectors in your retina, right? So the way that frog sees the world is very different from the way I would see the world, and the way I see the world looks really lame to that frog because where are the bugs? Like it's totally useless, right? So in that sense, sure, actually most of the functions of vision are tailored for an evolutionary goal, and whenever we take a computational approach to vision, we should keep that in mind, and that this will bend our even the way we approach the question. So now I want to take a detour in Gestalt psychology. Why? Because Gestalt psychologists are a dead breed of psychologists. They are like dinosaurs. They're gone. But they touched some concepts that are quite useful and could return somehow in even computational notions of vision. They are basically three Germans. I believe all three are German Jews. These are three brilliant minds that made this thing called Gestalt psychology. Gestalt is a German word, means like silhouette or a whole. It's one of those words that are impossible to translate. And the idea is that vision is not just a a bottom-up mechanism. You don't start with pixels and build the image by putting pixels together. You have big picture. You're looking for gestalts. So do you see the dog? Everybody sees the dog here, right? That's a famous case. So let's try this one. Who knows what this thing is? Rosa knows, so don't tell anyone.
You know, I lost it. I've seen it once and I lost it. That's
okay.
Annoying.
That's good.
So I know what it is and I can't see it.
I know what it is. Can I guess?
Yes.
Is it a cow?
Oh la la! Good job. Good job. Good job, Amanda.
Thank you.
Who else sees the cow? Oh yeah, Malcolm sees the cow too. Yeah.
Once you mention it, it's hard to not see it.
I had also
the cow, right?
I didn't know if it was a cow or a donkey, but yeah, I was there in the zone.
Okay, good. So the idea is that the way you organize this messy signal is by basically fitting it into a mental model, into a model. And when we say computation, we should think about what computational model can really do that job. And in a sense, this is the organizing principle of this whole course. We'll get back to that notion over and over and over. They also have this other demonstrations, this idea that you can infer a surface from where this is getting cut. How? Because you have assumptions about how the world behave, how like you have this assumption of continuities. That snake-looking thing, like one explanation is that those are three different pieces, but they align pretty nicely. So you can fit a snake model on top of it. And now how do you explain that part of it is gone? You put a surface, like a liquid surface on there. So all of a sudden you see a snake in a water, basically. I'll get back to that. This is another interesting Gestalt observation, multi-stability. Again, it's related to that notion that how much of vision is from outside to inside, how much of it from inside to outside is the stuff that you appoint, you assign to the signal. So that's face-vase illusion. You see two faces or a vase and you can switch between them. The Necker cube is one of my favorites. You can see that cube two different ways. Everybody sees that two different ways, right? You can switch. So this is where the signal does not constrain the 3D shape of the object, and you can solve the inverse problem in two different. The inverse problem give you two solutions in this case, right? And you can go on to either one of them. This is Gestalt law of continuity. You make the assumption that continuity is basically a feature of an object. So if you have those, if you look at the top picture where the two bottom and top outlines are separated, you see them as two separate outlines. If you go down there, you see them as separate objects because you group them separately. And the symmetry is another cue that you use. And I don't want to spend a lot of time on Gestalt. This is a slide that basically summarizes the other stuff, the things that Gestalts were interested, like the idea of closure, proximity, things like that. Sorry. Okay, before moving on, let me show you this one too. I don't know if the video will work. Let's try. If it doesn't work, I'll send you a link. This is bar cross illusion made by two good friends of mine, Gideon and Peter. And if I manage to share another screen with you guys, okay, there we go. So now we go here. All right. Do you see my screen? Yeah. Okay. So tell me, what do you see? This illusion is like a Zen practice. It's like you get master of your mind. I can't hear anyone. Unmute yourselves.
It kind of looks like something's rotating.
Aha.
I see two things going like this, like two things going like this.
At first I saw like it being like two crosses that kept like filling up in different space, and then after a while, now it just looks like an oval that's rotating.
I saw that, but
I cannot see the rotating oval. I can only see the things shrinking and getting taller and shorter.
Okay. Good. So this matrix of numbers, this dynamic matrix of numbers that has time too, that is going into your brain, has four possible explanations about out there. Explanation number one, it is one fluid cross. Its legs getting shorter and longer. Oops. Again. So its legs are getting longer and shorter, right? It's a liquidified cross. The other explanation is that there are two bars on top of each other, and they are getting short and long, independent of each other. Short, long, short, long, short, long. The other explanation is that this is a cross-like aperture. It's like a cut. It's a cross-like cut in a piece of paper, and you are looking at a rotating ellipse through it. There is an ellipse, it is rotating, and you're looking through that cross-like aperture to the ellipse. And the fourth explanation is that it's a solid cross. It's a solid black cross. The cross is not moving. There is an ellipsoid aperture that is rotating.
Well,
right?
Okay, I just got the rotating ellipse.
You got the rotating, the black ellipse.
Yeah. Behind four squares.
Yes, exactly.
Okay, so I have the rotating ellipse above the cross.
Right. Oh, I have a rotating ellipse behind, behind four squares. Like there's a surface above it, and then there's a black ellipse behind it.
Right.
We're rotating clockwise.
Yeah, but then there is this. Yeah, but you can even try. This is Zen. Control your mind, and then you can see the ellipse in front of the black cross. So the cross is solid. The cross is not
Whoa.
moving.
Okay.
You saw
Yeah,
it.
I see that now. I see that now.
Yeah. Okay. So this is. So now let's go back to the slides. Where did I? Here we go. Okay, so what I want to conclude up to this point, what I want to communicate up to this point, and if you grab that concept in a deep way, I will be very happy for this session. This is what we achieved, is that vision is an active process. Vision is not a passive process that reflects the world out there. Vision is very active. You are actively making up stuff in your brain. That's what your brain does. The scene that you see is an amazing creation of your brain. It's like, okay, put people in there, because if you lose those neurons, you don't see those people anymore, right? So basically you're having these operators that are making an active model of the world every moment. Like right now, actually, let's stop sharing again. And I can't stop sharing now. Oh, man. Okay, there we go. So look at me. This is the easiest demo, actually. Look at me. If I turn on my chair now, and you realize that, oops, I was a hollow surface all this time, like a two-dimensional hollow half body, right? And the back of my head is empty. If I do that, should I do that? You would be really surprised if you see that, right? Why surprised? You haven't seen it yet. It could be like that, right? There is no evidence. I have not given you any evidence that back of my head is actually full, right? But you have a model of me. You have a model of a human being, and you're perceiving this input signal by that. You're fitting that model to it, basically, to understand it, to make sense of it. And you're stuck with your model. We are stuck with our models. That's how we see the world, and we are forced to see the world like that, in a sense that these templates, or I don't want to say even template, because it has a baggage, it has a definition, but these models for understanding the world, or they come with a cost. They come because they come as a result of a bunch of assumptions, right? So now I will wrap up by a few more examples. One is the idea of invariance. The idea that you have the signal and you want to pull out the invariance of that signal. Basically, that matrix is coming in. You're looking to find out what is invariant in there, and these numbers are changing. But look at that circular thing. It moves around, but it is there, or the relationship between those two circular things are always there. What is invariant in there to harvest? So I use this concept of state space a lot in this course. So let's use a little bit of time to define it, and we will use the concept for many of our basically conceptual ideas. So imagine a patient comes into a hospital, and you have three measures from the patient. You have the temperature of the patient, you have the blood pressure of the patient, and you have the blood sugar of the patient, let's say. And you are monitoring your patient. These are the three measures that are more important for you, and as a doctor, you are monitoring the patient. So you can represent these numbers in a state space. State space is made when you give a separate dimension for each one of them. So you are independently measuring each one of these three dimensions. Now you have a three-dimensional state space for temperature, blood pressure, and blood sugar, a point in that space is what? Is the status of your patient, right? So this point describes the status of your patient, and you can actually track it down. You do measurements, like you go tomorrow, let's do another measurement. You get there, okay, fine. Another one, another one, another one, another one. It's a natural phenomenon, right? So it varies a little bit, but it remains roughly in the same part of the space. That's the interesting part of the space, the part that you want to keep the patient in there, right? So, so imagine one day you come and find out that the patient is over there. Oh, we've got a fever in addition to a high blood pressure. So what does going to that part of the space mean in a medical sense is one use of such space, right? So imagine this means another thing. This going in every corner of that space means a different condition. So imagine one day you are in here and you get that the temperature is room temperature. Sorry, your patient is dead. So basically parts of that space actually are life is not possible in some parts of that space. So life is constrained in a subspace of that space. These are the things that you can do with a state space. So with a state space, you can make up a neural state space. You can make like neuron 1, one dimension, neuron 2, another dimension, neuron 3, another dimension. Is there anything that stops us mathematically from adding dimensions to this space? No, you can have a 1 million dimensional space. It's just that we can't show it. We can't show more than 3 dimensions. I mean, technically now I have only 2 dimensions on your screen. Even that neuron 3 is cheating because it's not a 3rd dimension, but we can imagine multiple dimensions in a point in that space, in the neural state space. This is also something I want you to be on top of it, because this is a terminology we use a lot. This is a tool we use a lot. A point in that space, what does it mean? It is the descriptor of a state of all of my neurons, right? For example, let's say how many neurons are in my head? In the order of 10 to the power of 11. So make a 10 to the power of 11, how much is that? 100 billion. So make a 100 billion dimensional space. Each dimension of that space is a neuron, is a activation of a single neuron in my head. A single point in that space is my state of mind, is where I am, is who I am in a sense. And as I talk, as I live my life, as I do different things, that point moves around, right? Visits different parts of this state space. And that is a language that we will get back to a lot in actually early future. So now imagine I show a frog and record from these neurons and find out that, oh, okay, that point is where the frog lands. It activates neuron 1 X amount, neuron 2 Y amount, neuron 3 Z amount, a bunch of numbers. I show another frog, the frog ends up in a different part of the state space. It means that it creates another pattern of activation on my neurons. Another frog goes somewhere else, another frog goes somewhere. So I want to find a computational tool to recognize frogs. So can I make a circle around that part of the space and call whatever that goes in there a frog? That's the goal, right? That would be an easy readout from the brain. Well, the problem is that there are other stuff other than frogs in the world. So let's say we get a donkey. And the donkey number 1 ends there. Donkey number 2 goes into the frog land. Donkey number 3 is there. So now these two are mixed up. So if I draw a circle around donkeys, the circle will overlap with the frog circle. And it's actually worse. There could be other stuff like that pattern of noise might end up there in the donkey patch, right? In the donkey subspace. So how do I deal with that? The idea the idea, this is the idea that I'm borrowing from Jim DiCarlo. This is from DiCarlo and Cox paper, 2007. The idea is that a good neural space is a neural space that frogs and donkeys are easily separable in that space. That all the frogs go into one part of the space, all the donkeys go into one part of the space. In this case, in this example, you've got two individuals, two different people. And you want one of them to be in one part of the space, one of them to be in the other part of the space, so you can easily separate them and find out who was out there on the retina, on your retina, in the real world. But what happens is that in reality, what you usually get is something like that. So each one of these, let me go back to this. So let's again basically agree on words and terminology. You see that blue curved surface. Let's call that Sam's manifold. That manifold or that surface is all the spots that Sam visits in the state space. If you show Sam from front view, it will be one of those points. If you turn his head around, it will be another one of those. If you turn his head the other way or get him farther away or closer to your eyes, he will visit different parts, a subspace. That subspace is called, let's call it the manifold for Sam. And you will have another manifold with someone else. The problem is that when you are on the retina, on the actual pixel space, or in the actual space of the matrix that comes into your eyes, these two manifolds are entangled into each other. There are instances of Sam that are very different from each other, and there are instances of the other individual that are close to Sam or similar to Sam, right? So for example, I mean, you take a frontal view of any face, right, with a given size. Take a picture. They all look the same to each other compared to a face that is far away, turned like that, and half profile, right? So in a pixel space, those front views are more similar to each other, but you have to put together the front view of me and me far out there and me making faces all into one manifold and Sam in the other manifold, right? So how do you do that? That is the computational challenge of vision. Basically, when it gets those sort of detect the edges, detect the round things, those are perhaps the easier stages, but eventually we need to separate these manifolds so we can read them out. The idea is that as you go through the visual system starts from the retina, and we talk in details about these things in the course, but it starts from retina, goes to LGN of thalamus, visual cortex, early visual cortex, V1, V2, V4, IT cortex. This is sort of the standard hierarchy of the ventral visual pathway. So the idea is that when the signal enters the eyes, all these manifolds are entangled with each other. The eyes are sensors to capture the matrix out of the world. That's their job, and they do it geometrically, right? But now that geometric similarity is causing problems. That the way retina is basically dealing with the signal is causing problem for us because different stimuli are entangled on the retinal space. And the idea is that across these transitions, you take the signal from retina, give it to LGN of thalamus, to V1. In each transition, this space is warped a little bit. At each transition, you are warping the space in a way that you want to undo those entangled manifolds. What we get practically is that by the time you get to IT cortex, the manifolds are pretty separated from each other. The manifolds, the images, stimuli fall on well-behaving manifolds. So maybe another way of thinking about the computational problem of vision is to think about how you should warp your space to get the good stuff next to each other and disentangle the signal. So for example, here is another description of same thing. Subplot A shows V1 space. Like when you go to the early visual cortex, the manifolds might be slightly separated from each other, but they are still entangled. When you go to IT, you get pretty good separation, although even that is debated on like what kind of a stimulus are we using and what kind of question we are asking IT. But let's assume that's the case for the moment. And C shows a classical IT space, or the classical, more sort of old school way of searching for answers in IT. We used to go in IT, record from these neurons and say, I'm looking for my grandma. Where is my grandma? Is there a cell that responds to my grandma and no one else? Is there a grandmother cell? A cell like that alone would be like the plots shown to the far right, basically. That single cell, one dimension is enough to separate those two cases from each other. You don't need the other ones. But in reality, you need the other ones.
Mind if I ask a question about what?
Malcolm, yes.
Okay, so that just made me think about like at what point in time, like if we see two similar faces, at what point in time in our thinking are the two, like if we see two people and we think they look alike, is it because they were hard to linearly separate the two faces at IT, or is it because the matrix that came in was similar? And would that be something that you would study with like MEG or something?
Good question. Both. Actually, to give you a sense of how would that look like, it's actually you asked a very good question. So both. If you make two signals very similar to each other, it becomes harder to separate them, right? Like twins, identical twins are very hard to separate from each other, right? Because the signal is very similar. But assuming the signal is the same, your state of the mother of those twins have a much better time, easier time separating them from someone who is seeing them for the first time, because you train your system on those little dimensions that actually do the separation for you. You want to make a cut. So you kind of turn the signal around to find where should you make the cut. So you might find out that, oh, one of them has a little pigmentation here. I pay more attention to that. That makes the cut for me. Right. So and when you get more familiar with something, you know all these cutting points. Your visual system knows that. Like there is this classical example of the other race effect. They say like you go to a part of the world. It's actually getting hard to have the other race effect these days because the human population is getting more mixed up, and we see each other more. Thank goodness. But if you go into a community that in the old times they used the Japan example, like you go to Japan, all the Japanese look the same to you. I don't think that's the case anymore because we are more exposed now. Generally, a community of people who you have not seen them a lot, you don't have experience with them, your brain is also pushing them into one blob. You lose your abilities to discriminate. So what time is it? Oh, we're not bad. Yeah. So I land by bringing up examples of other cases of invariance. The example I showed you was a case of identity invariance. You want to warp the signal and do something to the signal to pull out the individual identities. You want to know which one is Arash, which one is Rosa, which one is Simon, for example, right? But that is not the only form of invariance that the visual system has to deal with. Actually, that one is a little bit of a luxury. That's a little bit of a high-level invariance. To see, we have to achieve low-level, more basic invariances. One of them is size invariance or size constancy. We just reviewed together, we just observed together that size is a hard to define concept in vision. A retinal size does not mean much, right? So how do I deal with that issue of size in the real world? Like, look at that. These two people are two people, I mean, roughly the same size. The guy looks smaller because he is further back, but they are people, right? The size of that guy on your retina is ridiculously small. If you move him close, that's the size of him. The size of, basically in both pictures, the man's size is the same. In one of them, he's standing further back, so your brain enlarges it for you. Your assumptions of size constancy enlarges it for you. Basically, size constancy is the Emerth law, is basically the idea that the size of anything on your retina makes sense only in the context. And constancy, achieving constancy means how to make the context interact with the stimulus, right? If that guy is standing that close in the corridor, he's going to be a Lilliput person. He's going to be a teeny tiny person, right? So you make him tiny. Moon illusion is an example of that. You have seen, all of you have seen, I'm sure, this amazing, beautiful rising moon of the rising full moon in the horizon. It's huge, it's big. When it goes up in the sky, it becomes small. And when I was in high school, my physics teacher used to tell me that, oh, this is the lensing effect of the atmosphere. It took me a long time to learn that it is not the lensing effect. The size of the moon in the horizon is exactly the same as the size of the moon up there. If anything, if you measure it with a telescope, up there is a little bigger than in the horizon. Why is the moon so big in the horizon? Because your brain, when you see the moon in the horizon, it's far away. It's behind everything you see in between yourself and the moon. All the buildings, it's far away. It's got to be a huge object that has that size. When it goes to the dome of the sky, you lose that background. So it feels closer to you, actually. So you perceive it smaller. And you can try this test with you. Next time you see a huge moon, make a piece of paper or like a banknote or something, whatever paper you have handy, roll it like a really thin straw, long straw, in a way that you can see only, it fits only the moon, and take away the background. Look through it, the moon becomes small all of a sudden, as soon as you take away the background from it. So that's another example of constancy of size. Another type of constancy, which is related to object recognition, but not identification, is shape constancy. Have you ever seen a rectangular door? I bet you have never seen it. I bet all the doors you have seen in your life were projections of the door picture. I mean, it's very hard to get a door projected onto your retina, which is exactly make a perfect rectangle. They are most of the time they are trapezoid shape. Like you are looking at the door at a slightly tilted angle. So the actual geometric shape of the thing on your retina is never a rectangle. But you perceive doors rectangular. Doors are rectangular, right? How do you do that? That's another one of those constancies. That's another one of those functions that you have to apply to the image to achieve constancy. Lightness constancy. We started with light and we are about to end with light. Lightness constancy is basically the idea that, all right, the numbers on that Mona Lisa matrix change. If you turn on the lights, the numbers all go up. If you turn off the lights, the numbers all go down. Are you interested in the exact number that is going from every pixel of Mona Lisa to your eyes? No, you don't care about that. That's not an important factor. What you care about is to know if that part on Mona Lisa's surface is white or black. What color is that? What color is the pigment, right? So you kind of want to get away from the variation that is induced by the ambient light, right? You want to take that away. And how do you take that away? You have a set of tricks to do that. One of them is to look at the contrast of the light with its background. So that's why you see the same pixels, the same gray pixels in the horizontal bar here. Some of them look, the ones to the left look brighter than the one to the right, because you're canceling out that effect from it. It is not only that. It is not only the effect of light coming at. There is also the effect of background, the effect of things that could be on your way. The pupils on the eyes of this drawing, the gray pupils. I wish I had my pointer. They are exact same gray, but they look different to you because of those assumptions that you're applying to. The point, we will go into the details on this. This is just a tour. Point A and point B are the same gray, right? But why do you perceive point B white and point A dark? Because point B is under a shadow. So you kind of take away the effect of shadow. What you want to really know is that a white surface or a black surface? Imagine that's a chessboard and you have chess grids made of ivory and ebony, right? You want to know if it is ivory or ebony. And you turn the light really high, even the ebony part could be as bright as the ivory one. But at that time, the ivory is shining bright. So you have to do all the calculations. Your brain has to do all the calculations. What is the color of the other one? Is there a shadow here to compensate for? So the illusions, basically, what I am trying to communicate is that the visual illusions that we have are not there because the eyes are bad or we are basically messing up something. It's because they reflect a function that the eye actually has to do in the real world. There is this other notion of color constancy. We will have a full session on that, on color, to just give you a taste. Oh man, how can I describe this without a pointer? So you see this cube, this like Rubik-like cube. On the top surface of the cube, at the center, there is a brown grid, right? There's a brown block. On the other surface that is under the shadow, the front surface that has a shadow on it. Yes, Rosa, thank you. Those two are identical, the same color. Can you believe that? I mean, the pixels that go into your retina are exactly the same. One of them is bright yellow, one of them is brown. How so? You are calculating you are making a whole model of the world in there. You're making a whole model of the world that is basically, there's a cube, light is coming from the top. So whatever that you see in there is basically less bright, or the shadows, this part of it is under the shadow. So whatever you see in there is actually more bright than what it appears. And once you do all those calculations, you get those two numbers. And if you cover up the background, those are identical patches. They are not different at all. Here is another example, which is not about modeling the light coming at objects. It's about modeling the light going through filters. Your brain even modeled that. So one seems to be going through a yellow filter, one blue filter. And again, can you believe that this one, you are not going to believe me. Rosa, can you show that? So actually, even Rosa doesn't know it. Even I don't know it. I have to think about it. Like I had memorized it, that which one is which, because it's unbelievable that blue box on the corner of the one in yellow, the top surface, yes, that one is the same as the yellow on the other guy, the second from the corner. Yeah, can you believe those two are the same? No way, right? No way. They're great. They're both great. And you see one of them yellow, one of them blue. Why? Your brain is making things up for you to make sense of the world, to make sense of this signal. And this is also another amazing one. I love visual illusions because they inform us about the assumptions of our visual system. And they tell us the tricks that we are using to solve the real vision problem. So on the very left, you see a lightness error, right? So she seems to be covered up by a film, semi-transparent film, half of her face. So if the gray of her pupils are the same, and one of them is filtered by a dark filter, that eye is going to be brighter in reality. So your brain undoes you undo the effect of the filter and make one of them look brighter, because it gotta be brighter if it is the same luminance on the retina. All the pupils of all three individuals here you see are the same, basically the same color between the two eyes. Here is the one, is this one. The other one is unbelievable, right? Again, like one of them is orange, one of them is blue, but they are both same color. And so this is the last slide I'm going to show you today. And this is the most amazing visual illusion you have ever seen and you will ever see. The illusion is, I want to say, designed or suggested by David Field, and summarizes a moment of epiphany in my life when I was at a talk by David, and he just made the claim I made. He said, I'm gonna show you, next slide, the most amazing visual illusion ever. And my reaction, coming from the vision lab, I come from a vision psychophysics background. I've seen lots of illusions. So I was like, oh, okay, one of those claims. Again, he's making a claim. Fine, let him show the illusion. And then he showed the darn most amazing illusion I have ever seen. And here we go. Here we go. This is it. This is the illusion. Those two blocks on the left and right look identical to you. That is so amazing because they are as different as two images can be. I showed them back to back. This is one of them. This is the other one. You see the difference. Actually, one of them is the negative of the other one. That's how I made them, right? So for a computer, that is the easiest thing to do. The easiest thing to do, to see the difference between these images. On the state space, actually think about it in the context of a state space, right? On the state space, every point which is white on the left one is black on the right one, right? So they're on the corner of the state space, as far as possible, as they are on a diagonal of the state space, as far as two images can be. A stupid barcode reader sees that difference easily. You don't. What's going on? This shows how much you have traveled from your retina to whatever that is the basis of your seeing right now, whatever structure in your brain that you are reading out to perceive the world around you right now. The space is so warped that two stimuli that are quite disentangled from each other at the retina, right? At the retinal level, these two are super different from each other. To disentangle the rest of the world, you have warped this space so much that at the end of the day, those two super simple stimuli are so hard for you. They are crushed into those two diagonal points of the space, pixel space, are warped now, are pushed into one little corner space. All noises go there. Noise, another noise, send it there, right? They're all different, poor guys. But you don't care about noises. Back to the question about evolution. Who cares about noises? You care about other things. So you expand other parts of the space, warp it to make it separable. And it comes at the cost of crushing other parts of the space and squeezing it. And basically, back to the example that I was bringing earlier, is the idea that now if you look at me, If you look at me and I turn around and you see the empty, you see that I was a hollow surface, you would be surprised, because you are looking at me with all your assumptions, with all your prejudgments about a human being, and that's what you see. That's what you see, not the pixels that are hitting the retina. So I finish at this point. The plan was 5 to 6:30. We are good. Questions, please.
I have a question. It's actually a thing that was way back in the beginning, but it was an image of a vase and it had the silhouette of two heads at the side.
Rebecca, right?
Yes. Hi, my name is Rebecca. So I was wondering if there is an example of a blind person who obviously has no vision, has never seen a face before, and then was able to see, looked at that image, if it would be possible through their sense of touch when they were blind, those two faces. And so it goes into a deeper question, which is how are other senses participating in the perception of vision?
It's a very good question. Unfortunately, we don't have the answer to it. We don't know. We don't have enough studies in there. But there surely is interaction with other senses. Actually, in some sense, the notion of reality is a consistent explanation between your senses. Let me unzip what I just said. So how do you know what is real, what is out there? How do you know? Like the table in front of you, right? How do you know what is its size? What is its, I mean, is it real? I mean, you have a model of it in your visual brain, right? That is explaining all the light that is coming to your eyes. But then you touch it too, right? So your explanation at the end of the day should explain the touch, the vision, basically all of your senses about you should come up with a consistent explanation of those, and that makes up your reality, basically. And in the cases that you don't have that approach, you don't get consistent representations. Like, here is an example. Actually, I was at the dentist office today, and this is sort of a fresh experience for me. I had this cavity in my one of my molars, and I was like, I used to feel it with my tongue all the time, right? So you stuff that the cavities in your teeth or like burns in your mouth, you feel it. They feel really big. But when you see them, the dentist opens up and take a picture, and it's a teeny tiny hole. So the sense of the size of that hole, which is created by your somatosensation of the tongue, right, is not calibrated with that of vision, because you never see that. Had you seen it, like I see my cup all the time and I touch it, so this is a calibrated sense, right? My two senses are calibrated with each other. For those, they are not calibrated with each other. So in a sense, we have to calibrate all of our senses with each other and make them consistent. And we have to even calibrate our motor system with them and make it consistent, right? Because again, remember, you are just born in your Platonic cave, in your skull, right? So what you get is a bunch of numbers that are coming from these cables, sensory nerves, and a bunch of numbers that you send out, the motor nerves, right? Have you seen like 2 days old babies, even like 1 week? When they're lying on their back and doing these random jerky motions, like really random. Every time I see a baby like that, I'm like, oh, they're calibrating their motor system, because that baby is born in the Platonic cave. He doesn't have any idea of what is happening outdoor and how do I interact with that, right? So you have to tune these things with each other, calibrate them with each other. To that, I am sure you have to do that. But how good you do that, what mechanisms are there to do that, I don't think we know.
Arash, on that note, there's an interesting miscalibration that happens when you're drawing. So let's say you're drawing your coffee mug. Most of the time, the retinal projection, as you alluded to in the shape constancy bit, the retinal projection of the opening is an ellipse, not a circle. And it's quite a narrow ellipse. And most of the time, the first time someone sits down to make a drawing of a coffee mug, they will exaggerate the opening of that mug. They will make it a lot more circular than it actually, than the retinal projection itself is.
Interesting.
The same thing happens with their drawing a door or a table. But basically, people, if they're not trained, they don't actually demonstrate good shape constancy when they go to make a drawing.
Right.
Which means that, like, somehow our knowledge about the sort of cold reality of the thing that we touch and that we use interferes with your ability to replicate it in the visual domain, even though we experience it both in the visual and the somatosensory domain. There's no like lack of information there. But you have to be essentially told, you have to be instructed. If you go into a 101 drawing class, they'll ask you to measure it with your pencil. Measure the height of the ellipse, measure the width of it, because it is really difficult to overcome and suppress.
They say it takes some time for the painting students to realize snow is not white. You should not paint the snow white, because whenever you paint the snow white, it looks lame. It doesn't look like snow, because snow has a lot of reflections coming off, right? A lot of things that are around it are reflected off the surface of the snow. And that's the matrix of numbers that go into your eyes. So if you want to mimic the snow, you have to paint it that way. But what do you paint? You paint the thing that is abstracted, the high level thing that is abstracted. You have abstracted the surface property of the snow, which is white reflectance, right? And you kind of make it white in your head. Now you want to paint it. You grab your brush from that high level representation, not the low level one. Shape, I believe, is the same concept. It's actually a good example.
Yeah.
All right. More questions?
I have a quick question. It's Amanda. Hi. So I'm trying to wrap my brain around, and the example that you're using, how we see you as a 2D shape or pixel or form, but we do infer that you're 3D. So my whole thought of this is, if you stuck, for example, someone who is an image analyst or someone who goes on Google Earth all the time in an MRI machine, and someone who didn't, so basically someone who really knew how to infer 3D shape from 2D shape, like what would you see, or how do you develop that skill, or what areas are involved? I kind of want to touch on that.
Can you explain more, elaborate a little more?
Yeah, so basically, I guess what I'm asking is, how would you train yourself if you were just someone who is interested in image analysis through Google Earth or whatever, any sort of 2D image forming into 3D shapes? Like what areas are most active, or how would you get better at inferring like spaces? So for example, I think a lot about buildings. So how people can look at what appears to be a square from the surface, but they could say, oh, I can tell how tall that building is, or I can tell the shape of that building in a more intricate manner. So I guess, like, can you just talk about that a little bit?
Well, there are two different things to consider there. One is that is there information in there, and you can visually train yourself to extract that information better. I'm pretty sure you can. And how can you do that probably depends on the exact task, right? The exact task at hand. So if you want to like discriminate the height, like tall buildings from short buildings, you got to be paying attention to the shadows or things like that, right? But at the same time, note that probably not all of them, not all of those tricks that you can learn are as easy for you, probably. there could be tricks that are equally informative but are hard for your visual system because they are not on the manifold of your visual system, right? Let's say there is a trick that I don't know, a computer can easily use because there are these different pixels, whatever, 10 degrees apart from each other, and they contain some information about the angle of sun or something like that. The machine could easily use that. You're stuck with your visual system, so you can't, not necessarily every piece of information can be harvested. I don't know, maybe another way of, how about this? This is the purest.
I was going to say,
Rosa.
I think the thing is, you actually, in the Google Earth situation, you don't have very much visual experience of flying over the Earth and seeing buildings at that view, right? Like in every other case, you have seen people, you've seen Arash, all like you can build the model of people because you interact with them. So I think you would just have to spend a lot of time flying over buildings, whether you do it in Google Earth or not, and then coming down from that viewpoint, right? To train yourself.
Yeah, and yeah, also again, actually that's right. The thing is that you don't have much of an invariance to begin with in a case like that, right? In my experience, the first time I flew in a small plane, I was like, wow, those things are too small. Like I lose my invariance. Objects on the ground becomes very small, and my sense of distance is crap because I don't know. I'm sure if you fly for some time, you will get better. Pilots are better in that. Pilots have even this. I don't know, like driving for me is a two-dimensional thing. I do left and right, but pilots do left and right and up and down. So it's kind of, you're getting to a cloud. Should we go on top of it or on the bottom of it? And this sort of this expands your sense of vision, and they are different. But I don't know if I actually don't know if there is any systematic way to do it and improve it on your own. I don't think that's Amanda's question. Any more questions?
This is Simon. I don't know. This is not really a question, but I wanted to know what you. So you were saying earlier, during while we were talking about questions, that agreement between senses is reality.
Right.
I kind of wanted to push back on that and say I think it's subtle, but I think important difference. I think disagreement between senses is unreality, just because if there's simply agreement between the senses, I don't think it necessarily means there is a reality. And you can also have a within one sense. I mean, the example you were giving earlier of if you turn your head and you turn into a shell, I guess that's not a, that can be unreality from just within one sense. So I think there must be some unified model there must be some unified space between all the senses that doesn't necessarily require agreement, but disagreement is a problem.
Can you explain more?
Sure. Well, so my question for you is agree or disagree. So the original statement was reality is agreement between senses. I would say that disagreement between senses is unreality, but agreement between senses is not necessarily reality.
I would agree with that.
Okay.
I would agree with that. Yeah. The agreement between senses is at least necessary, right?
Okay.
You need to make your different senses consistent, but I don't think the opposite. I'm not committed to the opposite. Yeah.
No, that was my question.
Although I would say you can explain that a little more for us, because that's an interesting thought, right? That it is possible not to calibrate two senses.
In what way?
And still have a reality, if those two senses are never compared with each other.
Right. And you could also have a scenario in which I believe a reality, even though I have, well, no, I can disbelieve a reality even without sense disagreement. Right? I can say this is a flying spaghetti monster, and I don't have to smell it to know that that's not real.
Right. Yeah.
So I don't know. I disagree with the strength of the original claim. I don't know if that's the only. That's like if this is like what reality is. I don't know. That's like a very strong claim. I don't know. I was kind of to chat about.
So let's do it from square zero. So how do I know something exists out there? Right. Whatever that is existing out there is a model that my brain has made. Whatever that I think exists out there, right? It's a model that my brain has created, right? And how do I know that model is real? It should work, right? It should work. I interact with that thing, and that's what I mean by making different senses consistent. The sound should be consistent with the images, the actions that I have. I touch it, I push it, right? So those should be consistent. And once those are all consistent, I guess that's as real as it gets. I guess that was the original claim.
Yeah. Okay. So then the question is, can we have a unreality where we have, a reality with disagreement? Is that plausible?
Good question. Let's think through.
Yeah. Is it necessarily an illusion?
So the cavity in the tooth is an example. It's real, but the two senses are not forced to make themselves consistent, right? Yeah. And it is real, it is inconsistent.
Yeah. To chip in maybe on the
Fernando.
Yeah, it's a very interesting point and a discussion. Clarifying what it is that we mean by the concept of reality is already complex enough, but assuming like a very kind of natural language kind of concept of reality, we tend to relate that to some kind of geometric description because you can link across modalities in a meaningful way in your high level kind of mental representation. Nonetheless, if you think about different kind of senses, they have peculiar spaces with peculiar features and idiosyncratic modes of representing things. And they are as real as it gets in their peculiarities. So there are like two different senses of reality. In one sense, they have nothing to do with consistency. And on the other one, they do. So in the more conceptual level, they have to do with kind of this intuitive kind of Euclidean geometric way of thinking about things. But on the other one, a taste or the unique things of the taste of pineapple, what are you going to confirm that against?
That's an interesting, that's Fernando, that's an interesting thought. So you are saying, I guess you are saying the higher level your descriptor is, the more of a concern this becomes. The lower level it is, the less of a concern consistency is, right? Because for a taste receptor, how can it be consistent with a photoreceptor? There's no way.
Not quite, sort of, but not quite, because the taste that you have, it is linked to receptors, but I'm pretty sure you can dream of taste just like you dream of light. So it's not about receptors, it's about the structure and the idiosyncratic aspects of that specific sensory space.
Right.
So when you have a taste, you don't share that with sight or hearing, but it is real. So I think that there is.
How about this? If you have a phenomenon that can have a non-zero projection on two different senses, then they have to be forced to be consistent. But if the phenomenon is projected only to one of the senses, the question of consistency is actually obsolete. Like the taste of pineapple, my photoreceptors have no opinion on that, right? They don't sense it. So they don't have to be consistent with the light that is hitting my eye from the pineapple. But what else? I mean,
yeah,
the pineapple falling and the sound that it makes, they should be consistent now because they project on both vision and audition. How about that?
That's a better one. You have like workspace of consciousness, you could call it, and if you are in the space where things causally interact, or you need to make them causally interact. I guess the criteria of talking about a notion of reality that requires to put these things into correspondence, I would think that would make sense. But still, that's like a secondary concept of reality. It's not it's a concept.
So what is the primary? What is the primary concept of reality?
That's, well, if I follow on the train of thought, I guess the main intuition about reality would have to do with, and this gets pretty metaphysical, but it would have to do with consciousness. And would have to do with, you know, having percepts. And I guess that you can have a huge space of percepts that are pretty primitive, and they are still nonetheless a reality.
So that space, that discussion gets philosophical really rapidly. So let's save that for offline, and we can digest, we can dissect it more offline. But basically, what I mean, I don't mean it in a philosophical sense. I mean it in a shallower term. Basically, what I mean by reality, I mean the pragmatic reality. The realities that your brain are working with are the ones that if they are, and I'm coming up with the formulation right now, actually, after this discussion. Does it make sense that if your multiple senses are affected by an incident, by a single incident, they have to find a way to make it consistent. If not, they don't have to. Is that a reasonable conclusion?
I think so. It's like, again, going back, it's like a narrative. So if you need to make a narrative because things can interact or seem to interact, then this kind of reality that requires to put things into correspondence kind of kicks in.
Right.
But
right.
It's it's one more aspect of kind of being, you could call it, if you get Heideggerian in a certain way.
Yeah. Okay, thank you. Any more questions? So this was this little discussion actually was a good taste of what I am hoping to have more of in this class. And before saying goodbye, I should mention again that I don't think this is a one-sided class, in the sense that I'm the radio station and you're just tuning in. I want to get feedback and pushback and discussions, and as you see in neuroscience in general and in vision science in particular, very soon you hit the limit of the boundary of human knowledge, right? So like question number 3, the answer is I don't know. Usually. So that means there is room for us to think about them, to formalize them, because we are the ones we are the generation that have to be, and I'm cheating here, I'm kind of putting myself on your generation as well to make myself look younger, but we are the generation that have to solve these problems. The ones that the answer to them is I don't know. And the way we do it is by dissecting them and turning them into concepts, making them measurable, coming up with experiment ideas and things like that. So I'm hoping to get more of this as we go along. Thank you very much. And if there is no questions, see you next week.
Bye. Thank you.
Bye. Thanks.
Thank you.
Bye. Take care.